Hi, everyone. Thank you for coming to a very special instance of the Space Science Seminar Series because we have two graduate students presenting this time around. We have Alvin Karimi and Hanieh. Alvin is going to be presenting first, and I think you guys would be very interested in these two talks because they have to do with magnetic reconnection, and that's a topic we hear a lot about. But I think both talks are going to talk about it in a way that is unusual or not the same as what you regularly hear in spaces like this. So some interesting different stuff. Yeah, and so first off, we have Alvin, who is a undergrad at CU Boulder, my alma mater, and now working here at UNH with Harlan Spence. And Alvin, if you can see the title.
Sweet, thank you, Robin. What an introduction, wow. Hi, everyone. Yeah, today I'm very excited to be talking about my research a little bit. And what I've been working on is investigating the magnetic fluctuations at dissipation scales in the pristine solar wind. And a big thank you to my advisors, Dr. Harlan Spence and Dr. Charles Smith, for all their guidance and help with this preparation of this presentation. Yeah, let's jump right into it. So in this talk, I'm going to give a little bit of an overview and introduction into turbulence, and then I'm going to jump into a little bit of our motivation behind the research that we're conducting. I'll go over some of our methods and analysis techniques that we use. I'll present some of that analysis here, and then I'll sort of wrap it up with a discussion leading into what this research can look like in next steps in future work. So when I kind of think about turbulence, the image in my mind instantly kind of gets drawn to Van Gogh's Starry Night. And it's an excellent depiction of turbulence in an artistic way. You see sort of these big cascading eddies or turbulent sort of rotations in the night sky that he's used with his paintbrush, and they sort of dominate this entire process here. And not only do they sort of, you see the different brush strokes as chaotic sort of twirling eddies like structures, you see how it cascades into smaller and smaller sort of eddies as the strokes and brush strokes kind of go on. And you can kind of think of turbulence in the same sort of way, or at least I think of turbulence in the same sort of manner, where we have these large scale structures that sort of evolve and change over time and fluctuate down into these smaller and smaller scale structures here. So turbulence in its most basic form can be described as the disordered fluctuations in the plasma. And like the Van Gogh kind of shows here, turbulence is multi-scale in nature, and I'll go a little bit more into that in this slide. When talking about the turbulence spectrum, these are the three main ranges that we're sort of looking at or studying. And at the very top, we have the energy containing scale. Now, this scale kind of acts as a reservoir of energy that essentially provides the energy in the flow in the fields at the largest scale. So we're talking about coronal structures, large, massive structures from the sun. And as the solar wind sort of travels out and propagates outward to the sun, we kind of hit this transitional range known as the inertial range. This is probably what would be considered the most studied range in the turbulent cascade. And you can kind of think of it as, or it could really be characterized as the scale where injected energy cascades from these large solar structures down to the smaller kinetic structures. It's that sort of, transitional range is a good way to think about it. It's good and important to note that the interactions at this range, so as the turbulent cascade is sort of getting into the smaller and smaller scales, in this range, most of the interactions are non-dissipative. And that means essentially energy is conserved from the transition process within this range. That, however, changes once we get down to the dissipation scale. Now, when we get down here, or when the turbulent fluctuations get smaller and smaller and smaller, to the point where they sort of resemble the scale of the ion gyro radius, for example, the energy and ions, or the fluctuations sort of interact with the ions at that point. And this is sort of where we see a drop off in the energy in the fluctuations and sort of an injection of energy into the particles, heating them. So this happens for the ions and the electrons, and there are different ranges which that happens. The ions happen first, followed by the electrons at higher frequencies. And we can see this in a steepening of the power spectra, which I have Here, like I was started describing, we have the energy containing range in the top left, where you see we have a lot of power at very low frequency, and as we transition out and propagate out from the sun, we get into the inertial range, the transition range, where we get a nice Kolmogorov power scaling law. And once we sort of hit the sub-ion/ion dissipation range, you can see that the spectrum steepens and falls out, and that's indicative of the energy being transferred from the fluctuations into the heating of the ions, and then further down you have the heating of the electrons.
I'm just gonna play the ornery old scientist in the room.
Yes.
The minus 2.73 power spectrum can be consistent with a loss-free cascade at those scales, but the steepening in the transition region, which exceeds that, is often attributed to ion scale dissipation.
Yes, thank you. So kind of going over to our motivation for this project, we want to understand how turbulence behaves in the dissipation range. Now, here's a nice figure provided by Bill Matthews and others that shows a sort of composition or a 2D composite image of the magnetic correlation function fluctuations in the solar wind as a function of distance. So essentially what you have here is a distance scale and the perpendicular and the parallel propagating components of the solar wind, and you have and the scaling is essentially in in tens and hundreds of thousands of kilometers. Sorry. So we're looking at the inertial range here, and Mathis was looking at this Maltese cross pattern in the inertial range. What we aim to do is sort of replicate that. Except look at the dissipation range, and kind of like I pointed out, the dissipation range happens at small scales. So we're looking, instead of hundreds of thousands of kilometers, we're looking more at hundreds of kilometers. So the range that we're really interested in is sort of in the middle of that cross right there. And we don't know how that behaves. Like I said, we are looking at, instead of scales, massive scales, we're looking at much, much smaller scales, orders of magnitude smaller. And sort of the third reason for this research is we wanted to sort of explore the behavior of turbulent fluctuations at these small scales in a multi-platform, multi-environment, and multi-particle system. Multi-platform turbulence inherently is sort of a interesting thing to study using a single spacecraft, but you don't really get the complete picture until you view it in multiple dimensions. So using multiple spacecraft allows us to get a more complete picture of the behavior of plasma turbulence as it transitions from scale to scale. Multi-environment. So our study is primarily conducted, or is completely conducted, in the ambient solar wind. But we also want to ask the question, how does this study change, or what is the behavior of small turbulent fluctuations in, for example, the ion foreshock region? How does it behave? And multi-particle. We want to understand how small particle interactions are influenced by these small turbulent fluctuations at small scales, and vice versa. How do the particles in turn interact and affect the behavior of these small scale fluctuations? So to sort of just like drive the point home, the previous study explored by Mathis and his Maltese cross really encompassed a big chunk of the inertial range, where we're looking at distances of tens of thousands and hundreds of thousands of kilometers. The area that we are very interested in is the transitional ion dissipation range and the dissipation range, which would have scale lengths of about on the order of hundreds of kilometers. So talking about some of the instruments that we're interested in, we wanted instruments specifically that had quick sampling rates and had high time resolutions. And the reason for that is, if we go back to this picture, when looking at the inertial range, we're talking about timescales of data timescales on the order of hours to even days, even weeks. In order to sort of penetrate the small scales that we're looking at, we need to go with the assumption that we know that the large scale fluctuations over short intervals really sort of behave akin to contributions to the mean field. So in order to do that, we need a instrument that samples things at high resolution and gives us a good cadence of data. And for that reason, MMS helps provide that. So specifically, like I mentioned, MMS is we're taking data from MMS in the ambient solar wind, so anywhere from 15 to 25 Earth radii out. And we're particularly using the Fast Plasma Investigator, FPI, and Fluxgate magnetometer to measure the solar wind speeds, densities, and magnetic fields. In complement, we used ACE, which is upstream of MMS at the Lagrange 1 point to sort of validate our data, to make sure that the data we were receiving was in fact coming from the pristine solar wind. So talking a little bit about correlation functions, in order to conduct this study, we utilize these a lot. For the purposes of this talk, I'm only going to be featuring our analysis with normalized autocorrelation functions, which generally are able to give us the shape of the turbulence and the decorrelation of the magnetic turbulence without sort of that excess power associated with the unnormalized correlation function. But we did do different studies with the unnormalized correlation function structure, second order structure functions, and then we did relate it a little bit back to the power spectrum, but that will be saved for the paper that we're trying to write. But for the purposes of this talk, we're going to be talking about the normalized autocorrelation function. So knowing all this, our methodology when it came to choosing a data set and analyzing it was it had to be in the pristine solar wind. We wanted to validate that with ACE, which we did. And secondly, like I mentioned, we wanted to take high resolution, quick cadence data intervals. So for this reason, we decided to take our 4 hours of data on that day that we chose, and we separated it into 20-second intervals that gave us enough time resolution to sort of resolve the correlation function at these small scales. It ended up being around 720 intervals of total data, which we then took and transformed from GSE coordinates into specific mean field aligned coordinates, where Z was the mean field aligned coordinate. Z was the direction of the magnetic field mean aligned. So that was the compressional component. Y was the Z component crossed into the XGSE plane, and then X was just the completion of that orthogonal right-handed triad. And both X and Y were, of course, the transverse components. So here I have shown like a 20-second interval of one of the 20-second intervals of data that we took, and it can reveal some interesting things just by looking at it. So first, we have that green line, which represents the correlation length. Standard, since this is normalized, we used the correlation length as 1/E, which is sort of the standard. And in all three components, X, Y, and Z, we see that the turbulence sort of decorrelates around, a couple hundred kilometers, which does place this specific interval within the dissipation range. Of note is not only do we look at how far the correlation function sort of decorrelates out, the distances, the spatial distances, but we also want to take note of the shape. The shape of the decorrelation shows us how the plasma is behaving in that moment in time in the specific component when it decorrelates. So the two transverse components, you sort of see a nice smooth drop off, and in our compressional component, you kind of see what looks like a little bit more of a inverse exponential. Now, we took these 720 data intervals, and we summed them all into a single plot based on their component, and then we found their average. And this is what we found for a 4-hour interval of time. And in this case, we see that the X component does not reach decorrelation within our observed interval. That doesn't necessarily mean it doesn't reach decorrelation a little further out, but at least in our 20-second interval of time, given the spatial lags, we don't find that. However, in our Y and Z components, we do see that within this 4-hour period of time, the average interval does decorrelate. So taking us back to our goals a little bit, we wanted to find out how does turbulence behave at this dissipation scale. So we pulled some data, some magnetic field data from the ambient solar wind. We sort of talked about what it looks like in the inertial scale and how we wanted to find it in these smaller scales. And then we produced these summation plots showing what we found within a given 4-hour interval. What I haven't really talked about and touched on are the cone angles. So cone angles can be thought about as the angle between the interplanetary magnetic field and the solar wind radial direction. And when talking about turbulence, the angle at which it's correlating or decorrelating is something that's sort of essential to understanding the nature of the turbulence. So given this 4-hour interval of data that we had, in each 20-second interval, we found a angle theta, the average angle theta that the interval was sort of pointing in, and we have it plotted here. So the distribution covers 0 to the perpendicular fairly well, with the exception of the lower angle bins. But we found that this was a fairly good sample of data to do an analysis on. And what we did with these angles is that we took each interval and based on if it correlated or non-correlated, put it into a specific bin. Once those were sort of organized, we took all the functions that were correlated and split it into their respective angular bins. So if it had an angle of 0 to 5 degrees, between 0 and 5 degrees, we put it into that bin, and so on and so forth for each component. And what we found, given the entire analysis, was that the correlation function in Y and Z particularly tended to decorrelate faster spatially the closer to the perpendicular the angle, the correlation function was found in. So you can see in Y and Z, over here we have 25 to 30 degrees, in the middle we have 50 to 50 degree angular bins, and in the far right, we have 85 to 90 degree angular bins, and we sort of see this increasing trend in decorrelation, which is essentially the turbulence reforming itself on shorter and shorter time intervals. Also in our analysis, we found that our Z component, our compressional component, decorrelated faster on average than either transverse component, which provided an invaluable insight into how the turbulence is decorrelating compressionally versus transverse.
I should have asked this question a while back, but
Yes.
Of the two transverse directions, what are X and Y supposed to represent?
So X is, or Y is essentially the transverse non-radial component, and X is the transverse radial component.
Okay, so this is effectively GSM or
It's just rotated to the mean field.
rotated to the mean field.
Yes. Mhm.
Yeah.
And so some of the things that we could kind of talk about as far as like what we've accomplished in this project are, we showed that the analysis of short time intervals, that turbulence is decorrelating on the average of hundreds of kilometers, so we are working within the dissipation range. In addition, our Kona angle analysis showed that turbulence decorrelates at angles faster, close to the perpendicular in most of the components. And we have also done another study of a longer time set of data that I was not able to show here, but we also found similar results in that. So I think that was a 13-hour set of data. So at least between the two sort of samples, we've seen that as a trend. And in addition, when I look at future work, one thing that I want to do is I want to create sort of a 2D composite, like similar to that, akin to that of what Matthews had produced in his analysis. That unfortunately wasn't ready for this talk, but that is definitely a next step. And looking further to the future, we once again want to develop this further and mature it in order to do a multi-platform analysis. We want to characterize the correlation function in multiple plasma environments, and then we also want to understand the interactions between the energetic particles and small-scale turbulence. So thank you so much for your time.
We have a good amount of time for questions.
Just following up on Eric's question, so if the cone angle is 90, that means your X transverse component is 0?
X would be, so X is really just a completion of the triad where.
I guess it would minimize the X component.
Yes.
Okay.
And that could possibly be a reason why we don't see correlation or decorrelation in that component as much, but we need more studies to tell.
Okay.
I'm puzzled by something. If I were to think of your data, within the context of, say, a larger data set where you have the full inertial range of turbulence with fluctuations on hundreds of thousands of kilometers as you were showing, but then you're looking at, say, the individual spectra you showed were for short intervals. I can't remember the exact amount of time.
Yes.
Is it 20 seconds?
20 seconds. Yes.
And so for a solar wind speed of 400 kilometers a second, so that's like 8,000 or something kilometers, so very short intervals. The eddies of, say, 8,000 kilometers length in the solar wind would have a relatively small amplitude compared to the very large eddies. And so if you looked in the solar wind far from Earth, over an 80 or 8,000 kilometer distance, you wouldn't expect decorrelation because in order to really rotate the field by a sizable angle, you'd want to go through an outer scale distance of 100,000 kilometers or more. So is there something unusual about this solar wind interval? Like, could you be near the bow shock? Could your turbulence be different from pristine solar wind?
It definitely could be. So these two plots here show the interval of time. This is MMS, and then this is ACE data back propagated from L1 down to where we are at Earth. And based on looking at those plots and looking at things like electron density and number density, we didn't get too many indications that we wouldn't otherwise be in the pristine solar wind, but it is always definitely a possibility that some contamination could have happened from backstreaming ions or things of that nature.
There are two other follow-up questions I have. I can wait if other people have questions.
I just want to know what's the difference between just ambient solar wind and pristine solar wind?
I was using that as sort of an interchangeable term, so
Okay.
yes, that was just language on my end.
Okay. Well, sort of the little different, maybe different question, maybe the same question. The 20-second, we showed us the power spectra where against the frequency domain. I know it's not, maybe I'm having a hard time understanding the 20-second and how it applies to normalize the correlation function, but this, like, do you think the results of it depend on like what interval you choose? Because 20 seconds roughly correspond. I know it's not, magnetic field fluctuation frequency, but just converting that time scale to frequency, it's like 0.0205. But that puts it like way inertial range, but that, am I understanding this completely wrong? So to be able to resolve like the smaller scale, right, non-inertial scale.
Right.
Is 20-second okay, or would?
Yeah, so the idea and thinking behind that was essentially that we know that the large scale fluctuations sort of don't vary over very long time intervals, right? So if you have a large sort of like sort of turbulent patch in the plasma, if you look at such a small time interval and you zoom in, you don't really see like the large scale structure and the power sort of associated with that. So you're really focusing in on a specific sort of point within that turbulence. And that's how we're able to sort of find like the smaller scales that we're looking for, if that makes sense.
So can I ask a leading question, maybe help answer your question? 20 seconds is your total time interval, but how quickly are you sampling within that 20-second time?
Right, so we're using a 10% cosine taper, so we're actually, which is, I guess, typical in the field, but we're using a 10% cosine taper of out of our max lags of 20 seconds. So we're actually only sampling 10% of that. So it would only be sampling technically 2 seconds worth of data.
But how quickly does MMS, how fast is the cadence of your raw magnetic field data? How quickly does it sample?
Guess I can follow up on that. Is it burst mode or is it?
Oh, survey.
Survey, okay, so
Once every 32 seconds.
Yeah.
So
So one over your neck was screen with me.
Wait, 32 per second or once every 32?
One
Uh,
sample,
32 samples per second.
32 samples per second, yeah.
so the neck frequency is half that.
So, yeah, 32 hertz. Yeah.
Better.
I think it's 16 or like.
Okay, that makes it long.
So that-
Yeah, so good resolution.
Thanks, I felt like we should have all known that answer, so I was sitting here like.
Alright, we still have a few minutes, so.
So, a couple more questions. So one has to do with the Matthews Maltese cross plot that you showed.
Yes.
So one way, to construct these plots is, even if you don't have decorrelation down to the 1 over E level, just go out to some distance in the decorrelation in the parallel direction, say to 0.95, and then figure out how far do I have to go in the perpendicular direction to reach the same correlation level, and then you can construct kind of these contours like they're showing. But there's a way to also do it in 3 dimensions, and I wonder if you're aware of the work by Chris Chan et al. 2012, or more recently, Nico Siulis in 2024, where they construct the 3D coordinate system is a little different from yours. One is coordinates along the field, one is along the fluctuation direction. So if you took the delta B within your 20-second interval, the overall delta B, that would be a second direction. And then the third direction would complete the triad.
I see.
And then you can form a three-dimensional version of this. And the thing that's really interesting about that is it can tell you whether the structures are sheet-like in 3 dimensions, like current sheets, for example. Which people are very interested in knowing, is that happening or not? You have a great data set.
What is the 2024 paper you mentioned?
The first author is Siulis, Sioulas, first name Nikos. It's a higher order structure function.
that didn't work.
Thank you. Yes.
I have a quick question related to that. So given, if there is like a 2-dimensional field or like a quasi greater than 1-dimensional field at a certain time, and you take the mean field as like your z-axis, is there essentially a degeneracy in the x and y-axis, sort of? If there is a 2-dimensional field?
I don't think we've observed that.
Okay.
At least, yeah.
I also have a quick question. What made you choose cone angle as a way to measure the correlation scale, or like the turbulent structure size, as opposed to like clock angle or just BZ? So,
I think cone angle sort of gives a good representation of, how the turbulence is interacting and changing over a certain time interval. Because it is sort of the, it's, so cone angle is sort of like the solar wind, the magnetic field, the mean magnetic field in relation to the radial direction of the solar wind. So it made for sort of a, I guess, intuitive way to visualize it. Yeah.
Clock angle is relevant in the pristine solar wind because it's with respect to whatever magnetosphere the solar wind is running into.
Yes.
So do the open contours on this plot represent length scales that do not correlate? Or that do not decorrelate?
From my understanding of what he did, they represent the contours represent areas where there is a decorrelation or where the turbulence is reforming, but or maybe not.
They're just like level lines of correlation.
Okay.
I just don't remember which one is the 1 over E.
So if you went from ion scales to electron scales, would you learn something more? If if the fluctuations are already decorrelating at ion scales or larger, if you use burst mode data, for example, and looked at included electron scale fluctuations, would that ever change your results at all?
I'm not sure, I would feel like, yes, if we had enough high time resolution data to do that, or enough burst mode data to do a sort of complete study of an hour or so, it might, but I'm not entirely sure.
Okay, if you get to that point and wanna do it, let me know.
Will do.
And I'll help you.
Thank you.
What's the longest typical period of a burst?
We have hours of data in the solar wind, yeah,
Continuous.
continue, yeah.
That'll be interesting.
All right, thanks, everyone. Thank you. Well, Jason switches it over to the next presentation. We'll invite Hanieh up.
Also, guys, there's lots of pizza in the back.
Yes.
Here. Eat it.
While this is happening, I'll introduce Hanieh. Hanieh, is pizza's more important. Sorry, Hanieh. Hanieh is also a third year, right, grad student, at UNH, just like Alvin. Did her undergrad at Isfahan University of Technology and is now here at UNH working with Matt Ardall. We'll give maybe a couple of seconds for anyone else who wants to grab a single slides, and we're good actually. And then we'll start off. Go ahead, Hanieh.
Okay, well, thank you. Hi, everyone. I'm going to talk about investigating the energy conversion during magnetic reconnection using non-Maxwellianity measures and relative entropy. So I'm going to explain a little bit of what is energy conversion and magnetic reconnection. Then I'm going to explain the non-Maxwellianity measures and the kinetic entropy, and some sort of talk about some kinetic physics indicators in lower order moments. And then I'm gonna explain a new term, as we call it, relative entropy, going into like higher order moments, and something called a higher order non-equilibrium term or coordinate power density term, and maybe end up at the conclusion and the future work. So magnetic reconnection, as a lot of us all know, is a fundamental process that converts the magnetic energy into plasma thermal and kinetic energy across various environments. And this process effectively involves breaking and rejoining of magnetic field lines. And they enable energy release without violating the Gauss's law. And this reconnection happens in a localized diffusion region at a microscopic scale, driving plasma outflow jets. In this presentation, we're going to solely focus on a collisionless reconnection because there have been a lot of advancement in both like kinetic simulations and in our observations, particularly for MMS mission. One of the key questions when it comes to reconnection is that how is plasma energized in the diffusion region? Kinetic processes in collisionless plasmas, such as magnetic reconnection, they create highly structured distribution function. And these are key to identify regions of energy conversion that facilitates plasma acceleration and thermalization. So there have been many parameters that we have used to identify kinetic physics, primarily focused on lower order moments, like velocity, temperature, and pressure. And the examples of that are the electron frame dissipation measures, pressure and strain interactions, agyrotropy, non-gyrotropy, and non-Maxwellianity measures. And while these parameters do identify known regions of the energy conversion, they're either constrained to mechanisms affecting only the first and second moment of distribution, or they have not been fully explored in terms of how they relate in changes in the distribution's shape beyond the second moment. Also, a lack of collision leads to non-equilibrium structures. Systems that are not in local thermal equilibrium, or LTE, I'm gonna say it from now on, they do not obey the laws of thermodynamics. So we need a kinetic field analogy for the energy conversion, equivalent of the first law of thermodynamics. We also know that in a thermodynamic system, useful energy stored in a system is lost to heat through changes in the entropy. So if we think about entropy as a form of disorder, we think of just randomly distributing all the particles, right? Right here. And then we can count how many ways we can interchange the particles. However, instead of counting the individual particles, we represent the particles as a distribution function. And in order to do that discretely, we break up the position space and velocity space into discrete bins as they are here. And therefore, this can represent our distribution function, and then we can count how many particles are each bin. And therefore, we have some sort of like a functional representation. And now, instead of counting, as I said, the number of ways we can interchange the particle, we can figure out how this distribution function is distributed in position space and velocity space. And so typically our distribution function is 6-dimensional, so we can break it up into the position space and the velocity space. And that's how we can kind of introduce our entropy both in the position space and the velocity space. In the simulation, we can represent these bins linearly, but in the way that we measure the data, it's logarithmically spaced. So the bins are not evenly distributed. Therefore, it changes the way that we represent the velocity space entropy. And we're going to talk about why I'm focusing on the velocity space entropy rather than the position space entropy density. But first, we have to know why we want to use the kinetic entropy. Kinetic entropy arises from the fact that the entropy is maximized in an equilibrium or a Maxwellian state. Therefore, the difference between a measured and equilibrium entropy or entropy-based non-Maxwellianity indicates significant kinetic effects with potential for energy conversions to take place. To understand reconnection at a kinetic level, it is good to examine entropy-based measures of non-Maxwellianity in a plasma distribution function. A non-Maxwellianity is a deviation of a local plasma distribution from a Maxwellian distribution with a matching density, flow, and temperature. And initially, there have been studies that they did assess this non-Maxwellianity and by Kaufman and Patterson, and they are based on the kinetic entropy per particle. I showed them here. We call them NKP. This measure has several desirable properties, such as it is dimensionless, it is non-negative, and it is becoming zero at a Maxwellian distribution, meaning that if our distribution is Maxwellian, then the differences are zero. However, it is also have some undesirable features, and one of them, and most important one, is that it diverges under a certain physical condition. The divergence of the Kaufman and Peterson non-Maxwellianity measure is attributed to a fundamental issue with kinetic entropy. When the plasma temperature approaches extreme values, and by that, I mean when the temperature mostly goes to 0 or infinity. The source of divergence also lies in the way that the kinetic entropy is defined. And the way that we define it is using a phase space integral that doesn't account for the coarse graining, involves dividing the phase space into cells of specific volume. And when either temperature extremes occur or our spatial grids are too fine, then the entropy can diverge. Another issue that we have with the Kaufman and Peterson measure is non-locality, meaning that the kinetic entropy inherently includes contribution from a spatial distribution of particles. And therefore, using this entropy that we have makes our non-Maxwellianity non-local in position space, and this is not ideal for our case because we want to study the local kinetic effects during the reconnection, magnetic reconnection. So in order to overcome these limitations, we propose a new non-Maxwellianity that is based on velocity as space entropy density. And that captures the local distribution in a more appropriate way. This new measure is normalized and it remains finite across all temperature ranges. And it provides like a clear physical interpretation of the non-Maxwellianity. Yes. More importantly, it also has all those desirable features that we had with the Kaufman-Peterson non-Maxwellian measures. They're dimensionless, they are non-negative and zero for a Maxwellian distribution, while they eliminate that divergence issue that we had. This measure provides a reliable way to quantify this non-Maxwellianity, making it a valuable tool to identify the kinetic scale processes and regions that dissipation occurs in the plasma. And these two, as you can see in these two ones, this is the MKP, and as you can see, and this is like a log of it, that how it will diverges. However, the way that we came up with our Maxwellianity, it shows that there's no divergences happening due to the log, so it's not going to go above 1. So this is a good thing that we came up with. We also can have another another way of defining the non-Maxwellianity, which can be based on our MKP, M-bar KP. And with that, we're adding like an R factor, which we call it a regularization factor that arises from graining velocity space. And this accounts for all the information loss the information that is lost during the coarse graining. So the next step after we introduced our non-Maxwellianity is to look at other kinetic physics indicators and see the relation of it and how they confirm our non-Maxwellianity measure. So for that, I chose one of the famous events, July 11th event, where the MMS spacecraft encountered an electron diffusion region, and it detected a tailward directed ion and electron jets. This is the path of specifically the MMS tree. So one of the indicators of kinetic physics that we can study is agyrotropy, or the square root of Q. Agyrotropy is a scalar measure of departure of the pressure tensor from cylindrical symmetry about the local magnetic field direction. Ordinarily, the electrons are well modeled as gyrotropic with a very small agyrotropy. So in another word, the agyrotropy is a measure of how much our pressure tensor deviates from being perfectly symmetrical around the magnetic field line. So as you can see, as RMS was going through the EDR event, we have some increase in the agyrotropy, meaning that our distribution is not gyrotropic and therefore it's not maximum. So and the next step that we can do is that if we look at this flow diagram, that shows that the energy can like electromagnetic energy, they can go into changing the kinetic energy, and that for us is J dot E term or Poynting theorem, or they can change our internal energy, which is the pressure strain interaction, which we're going to talk about in the next slide for it. So now we can look into how our internal energy and our kinetic energy is changing. And these are the changes through that time as it's going into the EDR. And the same thing is here for our pressure strain interaction. When we are in a non-LTE system, or a system that is not in local thermal equilibrium, a useful energy that is stored in the system is converted to heat via a heat flux density Q. And those pressure strain interactions terms, mostly pi d and pi theta. And this approach extends the first law of thermodynamics to the systems that are not in LTE. However, these are not fully account for the random energies in the system, which I'm going to talk about it a bit later. Other indicators of kinetic physics are DE, which is electron frame dissipation measures, which they highlight the current sheet and flux parallel regions during remagnetization. Another one is the Non-Maxwellianity, which measures the deviations of the distribution from an equivalent Maxwellian. So the difference between this and our Non-Maxwellianity is that we're looking at the differences of the kinetic entropy, but this is looking at the distribution itself. So now we can talk about, after we see that, okay, there are changes that are happening in our EDR, we can also examine our non-Maxwellianity itself. This first distribution is from the upstream and is taken from the earthward exhaust after the electron have remagnetized and become mostly Maxwellian. So we can see that our non-Maxwellianity is close to 0. The second distribution, if we go into the inflow, where parapotential structures generate a temperature anisotropy, and the entropy here is lower. However, the non-Maxwellianity is relatively large. And as we can see here, it is a bouncing back and forth in the inflow region. And it means that our plasma is kind of trapped in this region, and that creates like an elongated distribution functions. And that's maybe the reason that our non-Maxwellianity is very extreme. As we go into the heart of the EDR, the non-Maxwellianity is intermediate between the inflow and the Maxwellian distribution. And these regions of elevated non-Maxwellianity, as a whole, as we all studied, they can be related to kinetic processes during the reconnection. And it is consistent with our previous numerical simulations, which I didn't include here, and the other kinetic physics indicators. Therefore, it does motivate the utility of an entropy-based non-Maxwellianity measure as an indicator of the kinetic scale energy conservation, conversion, and dissipation processes that happens in the reconnection. This is kind of an overall of how it's happened from upstream and flow in EDR all together. Sorry. So as we talked about the lower order moments, I'm gonna go into higher order moments, but first we have to talk about the differences between a system that is in local thermal equilibrium versus a non-LTE system. The internal energy in both thermodynamics and kinetic approaches are associated with an average random kinetic energy of the plasma, as I've shown in these two. However, the internal energy is missing other forms of random energy, as I showed here, which J and K are the index notation, and V prime is the deviation from the average bulk flow U. And these changes in the random energy are responsible for changing the shape of the distribution. To account for the changes in energy beyond random kinetic energy, there has been a paper that was published, and they did examine the evolution of the kinetic entropy associated with the distribution of energy. So now we can go one step further and to by studying the time evolution of this kinetic entropy, we can derive a generalization of the first law of thermodynamics for systems that are not in LTE, where E gen and Q gen, they are the generalized internal energy and heat term consisting as sum of LTE terms, describing the evolution of the equivalent Maxwellian states and the relative deviation from that, which I showed them with these two here, which describes the energy associated with the changing the shape of the distribution function. Here, SVRel, this is what we now introduce it as the relative entropy, and this term quantifies the changes in internal energy due to variations beyond the ones that we considered in an LTE system. For example, they're beyond the, as I said, density, velocity, and internal, and velocity, and etc. This SVH terms also couples with the relative energy and thermodynamic heats through the vector heat flux, pressure strain fractions, and the higher order moments. So this diagram kind of shows everything that I've talked about. So if we are in an LTE system, and if we do some work on our distribution, we can see that our distribution size is not changing. However, if the internal energy has changes, we can see this is still in the LTE system. It would be like a change in the density, but not in the shape. However, if we go into the internal energy and look at the relative energy and the relative entropy, as I pointed out here, we can see that our shape of the distribution will change. So we call it, or we explain it, this relative deviation of internal energy and heat, which is describing the energy going into changing the shape of the distribution as P Hornet, which we call it higher order non-equilibrium term Hornet power density. It's a very long thing. This P Hornet can be used to compare the rate at which the phase space density evolves towards or away from an LTE to other standard power density. So it kind of shows how we're going towards or away from a Maxwellian distribution. We kind of did all the calculations for the relative entropy density and relative entropy density per particle, the relative entropy per particle. As you can see, for our EDR event, as we're going to the EDR, our relative entropy decreasing, meaning that we have a more non-Maxwellian distribution. And as we're like leaving the EDR, it's becoming, it's increasing, so meaning that it's becoming more Maxwellian. This bottom panel is our P Hornet, and it's the total derivative. And that is the sum of the partial time derivative and the convective derivative. And we can see that the partial time derivative, this one, is much smaller compared to the convective derivative, meaning that the relative entropy changes due to the spacecraft sampling different regions of space, not because the structures are changing in time. And so as here, the P Hornet term is like increasing, means that we're going towards non-Maxwellianity. And again, as the EDR, we're kind of leaving the EDR, we're going away from it. This is a quick simulation of the P Hornet term. The dashed line, I don't know if it's possible. The dashed line is kind of the spacecraft trajectory. The purple is P Hornet being negative, and here the green one is P Hornet being positive. And in the inflow, a region like just above and below, you can see that it is purple. So it means that it's about to become less Maxwellian. But we do see a lot of oscillations here and here, which we need more investigation in these areas. However, they might be likely due to the fact that the electrons are remagnetizing in the outflow region, and then they begin to gyrate around the magnetic field line again. So as a future work, the research that has demonstrated the use of non-Maxwellianity in identifying the dissipation sites. However, a comprehensive observational comparisons of different calculation methods are lacking. And there have been recent studies that link the distribution structures with the Vlasov equations, and it does suggest a potential advancement into understanding our non-Maxwellianity. Another thing that we are doing is that we're establishing a value range for our these energy transfer terms. In addition to the non-Maxwellianity, we're going to work with the relative entropy and the Horner power density, and we will apply to other electron-only reconnection events, and we will perform a statistical study. We will also look at reconnection at different regions, such as the guide field versus the non-guide field, symmetric, asymmetric, and we can also apply that to the turbulence as well, like the solar wind, magnetosheath, and things like that. But yeah, I guess that was my presentation, and these are the references, and thank you.
And Hanieh, we do have a few more minutes for questions, so open it up.
I came across some interesting work that relates to part of what you were describing earlier. This idea that sometimes called the Casimir invariance. So like the delta F squared, I think it fed into your MKP term or something. There are these terms that are, these quantities that are conserved by the Vlasov equation, and just like the entropy itself.
Yeah.
And this work is by Michael Nastek and Alex Sarkosian. And part of it's published, part of it's in preparation. And they're pushing this picture where that Casimir invariant cascades from large scales to small scales, just like energy and hydrodynamic turbulence, but it cascades in space and velocity space. And it's associated with a universal K⁻⁴ electric field power spectrum that could be maybe measured by EMS at it is something that would occur at really small scale, the final cascade going down to like the device scale. And I wonder if MMS might be the only instrument that is capable of testing this kind of work in burst mode, for example. You might be able to measure like Fermi power spectrum, something, and have some of those predictions. But if you want to talk afterwards, I could point you to that.
Yeah.
Thank you. Yeah, I don't know, maybe we can talk about it after that, see if that's possible to use the MS data for those.
Thank you. So you say that you're using the non-Maxwellianity as kind of like a measuring stick of when you're in dissipation regions, right? And if I'm getting this right, if I'm understanding it, the way you do that is you say like, okay, here's the dissipation region, here's the non-Maxwellianity, it goes up at that point, right? That
It's
kind of,
kind of like we're looking at the plasma itself and the distribution itself of the particles.
Right.
And it's just the differences of like, we do have our Maxwellian distribution. We know the highest energy. So we're going to compare that to the energy of this and the entropy of this observed distribution that we have. And then that'll give us the non-Maxwellianity.
Right. Yes, and so you're measuring the non-Maxwellianity.
Yeah.
And as the non-Maxwellianity increases, you say, yeah, that's an
Meaning
indicator of
that,
the
yes,
dissipation.
yeah,
state.
meaning that our distribution is away from a Maxwellian
Right.
distribution.
So my question is, if you were to only look at the non-Maxwellianity, you don't have the other plasma information, is like how would you identify dissipation sites just from that? Is there some threshold, maybe you could say, there's some reference distribution where the relative entropy between your distribution that you measured and the reference distribution is some level, and your non-Maxwellianity has surpassed that, and so you know it's a dissipation site,
Oh,
something
yeah,
like that.
and then it's like, that's one of the future works that I said.
Oh, okay.
Yeah,
I
I
missed
said, I guess I said, if I'm right, that there's a problem of like, there's a value range for the energy
Okay,
transfer
you're right,
that
yeah.
we are trying to
All right,
do, to have like a, like, right way, as you're saying, of like, okay, what are the ranges that we're looking at, when we're looking at the relative entropy and the non-Maxwellianity in comparison to the
Okay.
other ones. And I guess another thing is that there are so many different kind of events that we can look into and compare them, so I guess port shutdown would be different.
So, great talk. I was wondering, so the event that you had highlighted was a symmetric reconnection case.
Mhm.
So how would this measure change if you had asymmetry involved? Would it still be able to pick out the dissipation region? Would it look different?
I have not started look at the asymmetric kind of dissipations, but another thing that we can do is to see how the shape of the distribution is different from in a symmetric one versus an asymmetric one, and that would be a cool one to see the differences of the distribution and see which one is different, yeah, I guess.
And also kind of a side question, have you ever tried doing this for ions as well as electrons?
So that's another thing that I am doing too, exactly. It's like, there are so many things that are happening like right now all together one by one. But because I have like a fixed outcome of this event, I just showed it, but we're also looking at the ions as well. There has been some limitation to it because of the MMS kind of separations. But yes, this is also another thing that you can use it for the ions as well.
Any other questions? All right, well, let's thank Hanieh again.